Our first application of work is Hooke's law. Hooke's law was developed by Robert Hooke, who was a contemporary of Newton. Newton and he worked together for a little while, and then Newton started hating him. And there's a lot of dispute about how much Robert Hooke actually developed versus how much he stole from other people, but we won't get into that today. All right, so the force, Hooke's law says the force required by you to keep a spring in a compressed or stretched state is directly proportional to how far it is compressed or stretched. In other words, f of x is equal to kx. All right, where k is a specific constant for the particular string. So k itself is constant for each particular spring. Oop, I don't know why I put a C in there. Constant. There we go. Constant. Right? Now, the absolute value of k will be large for a very stiff spring. Say like in your car, like shock absorbers or something like that. If the absolute value of k is low, is small, it'd be a very, I don't know how to describe it, very loose spring. Now, my example of this would be a slinky. Right? A slinky is a toy that everybody loves to get because of the commercial, and then they get it and they find they can't really do much with it after a while because the spring is so loose, its K value is so low that once you stretch it out, it basically can't be used again. So that's a slinky. I always wanted one, and then when I got one, it was just never worked as well as they showed in the video or the commercials. So there you have it. So slinky, and even in a slinky dog, would have a very low K value, as opposed to a spring that's very tight or has a really high K value, say, in your engines of a car. That would be a high K value. Now, Hooke's law basically says, hey, if you want to stretch it out, then it's going to take a certain force, and that force is directly proportional to how far you're trying to stretch it. And so F of x is equal to kx. And in case you're interested, Hooke's law has a whole Wikipedia page, so that must mean that it's important, right? It's got a lot going on for it. All right, so let's look here. If we stretch your spring, so your spring has an equilibrium state. So if you just let the slinky sit there, it has an equilibrium. Now, if you stretch it out, right, if you pull it out, then that means that you're having a force that's positive. So F would be positive. So if you look at your force up here, if this is your force axis, then your force is positive because you're pulling it out. If you're compressing your spring, right, if you're pushing it in, then your force would be negative because you're pushing it and jamming it tighter than the equilibrium state would normally like. All right, so let's use this in an application here. Suppose that a force of 15 newtons is required to stretch and hold a spring 0.25 meters from its equilibrium, i.e. rest position. So every spring has a rest position. If you just let it sit there, that's where it rests. That's the equilibrium position. All right, assuming the spring obeys Hooke's law, find the spring constant K and how much work is done or is required to compress the spring 0.2 meters from its rest position, and how much additional work is required to stretch the spring 0.3 meters if it has already been stretched 0.25 meters from its equilibrium position. Oh my goodness. All right, so much going on. Okay, so let's start with trying to find K. What do we know? We know that force is equal to Kx. They tell us that they're going to stretch it 15 newtons, right? So there's our force. Or excuse me, 15 newtons is required to stretch the spring 0.25 meters past its equilibrium, right? Equilibrium position, guess I should say. Equilibrium position is 0, right? So the equilibrium position would be 0, right? You're just going to let it sit there, right? Okay, so we want to stretch it 0.25 meters, so that would be 0.25. And obviously we divide both sides by 0.25 and we get that K is equal to 60. And now remember what these units are. So 15 was in newtons, so it's newtons divided by meters. So K is equal to 60 newtons over meters. That's what they asked for. So there we have it. So in case you're interested, that means the force is equal to 60x, right? Or f of x, I should say. The force function. All right, so now for letter B, how much work is required to compress the spring 0.2 meters from its rest position? Okay, so we want to take this lovely spring, and we know that its force function is equal to 60x because we just found it. But now we need to compress it. So we have an equilibrium start. So your equilibrium is right here, right? Because it says from rest right here. So if it's from rest, that means that we're from equilibrium, from rest, right? Which is equilibrium. So that means that 0, right? So we're going to start at 0, but we're going to compress the spring. We're going to push it in. So since we're compressing the spring 0.2 meters, that means we're actually pushing it in negative 0.2 because it's a compression. If we were stretching it, it would be positive 0.2. But since we're compressing, it's negative. Actually, let me say it. Negative because of compression. So I had to write that around the letter B. All right, so then, well, we can integrate this. This isn't exactly difficult to do. So this is 30x squared, and we're going to take that from 0 to negative 0.2. Which would be, well, 30, oh, I'll just put it down here, 30 times negative 0.2 squared minus 0 squared. I mean, the 0 is kind of irrelevant. We all know that's going to be, but in case you want to see it, there you go. So 0.2 times 0.2 is 0.04, so that's 30 times 0.04, which is 1.2. So this is 1.2. It's joules, or if you like, Newton meters. Either one, whichever way you want to write it. All right, now, what about letter C? How much additional work is required to stretch the spring 0.3 meters if it has already been stretched? 0.25 meters from its equilibrium position. Interesting. Let's think about this for just a second. If we look at force as a function, force, and then this is x right here, we have F is equal to 60x, so it's doing something, vaguely like this. All right, so from 0 to negative 0.2, we went back and found this area. Right? And we're going from 0 to negative 0.2. That's why it's actually a positive number, because we're going backwards. So it was 1.2 joules. So that was the answer to B. For the one that they're currently asking us for, they're saying, hey, it's already stretched. It's already been stretched 0.25 meters. See that? So we're actually sitting here at 0.25. This will not be to scale, but bear with me here. All right, so you're sitting here at 0.25 right here. It's already been stretched that far. And you want to know how much additional work is required to stretch it 0.3 meters. Now careful, that's 0.3 meters past where it already was, not 2.3 meters. It doesn't say to stretch the spring 2.3 meters. It says to stretch the spring 0.3 meters if it has already been stretched 0.25. So we actually want to keep going. I'm just gonna, this is not really to scale, but bear with me here. Keep going with that force. And I want to go 0.3 meters past that. Right? to this new number. Hmm? Okay, so this is going to be 0.55 because it's 0.3 meters past 0.25. So then the work is equal to the integral, and we already know it's 60x. I mean, that we already determined for this particular spring. Every spring has its own K, and this one was 60. But we're going to stretch from 0.25, and then you have to be very careful with the English that's given. So in this case, we're going to go to 0.55. I'm just going to put it, I'm going to do it in a different color. 0.55 because this is 0.25 plus 0.3. They didn't say that they were going to stretch it to 0.3. They said they want to stretch it 0.3 meters. So you're going to stretch it 0.3 meters past 0.25, which is 0.55. All right. So yet again, I mean, it's the same integral. It's not exactly a difficult integral. The problem with these problems won't be the calculus. It's going to be the setup, just getting everything right. So the calculus itself is actually pretty easy. So it's 30 coming out x squared. I'm going to take that from 0.25 to 0.55. Which would be 30 times 0.55 squared minus 0.25 squared. We all have Desmos. We can make Desmos find this. You can just trust me. It's 7.2 Newton meters. Or if you like, 7.2 joules. Because everything was given to us in newtons and joules. Or excuse me, newtons and meters, which would make Newton meters. Or joules are unit. If you want to see it in Desmos, there it is. You can see that my integral and my after I've done the integration and substitution, that they are one and the same. Therefore, I know I integrated correctly. Not that I was really worried about something so simple, but there you have it.